quality control captivates your party patrol. Your mind, body, and soul flow. The bell tolls like the rhythm explode. Big, bad, and bold beat.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Now that we have basic understanding of Newton's law of gravitation, let's make it do some work for us. So we want to go from point R1 to R2, going up in the Earth's gravitational field. In that case, the work done by the gravity on the object that is moving is the integral from initial position to final position, and then the force time, or the dot product of the force and the direction of movement. Now, gravity in this case is of course towards the center of the Earth, so that's going to be down, while our displacement is up. So that dot product has to be negative. So we get from R1 to R2, and Newton said that G times mass of the object and then mass of the Earth divided by r squared. Then we have dr, and then the minus sign because the displacement and the direction of the force are opposite. We can bring the constants out, so minus g m mass of the Earth integrated from R1 to R2, and that's 1 over r squared dr. And when we integrate this, we get, we still have the stuff in the front, and then substitution from R1 to R2 of minus 1 over r, like this. If you take the derivative of this, you get minus r squared, or the original, and that minus cancels this one. So just to check that this is the correct form of the integral. Now let's put in the limits. Minus, or first of all, these two minuses cancel each other, so we just have g m me of 1 over r squared, no, 1 over r2 minus 1 over r1, which of course can be written as follows. Oh, that's R2. As you might have guessed, we are after the gravitational potential energy, and we are tempted to write that this is just the change in gravitational potential energy, where the U is the actual quantity, Gm me divided by r. But let's look at the signs a little bit here. So the work done by the object, is it positive or negative? We see that the R2 is larger than R1, and because it's in the denominator, it means that this is smaller than this one. So the whole thing, the amount of work, is negative. And now we are saying that while the gravity is doing negative work, the potential energy would be decreasing, and that is not true. If we want to stick to the convention that the gravitational potential energy increases as we go up, we have to put the minus sign here, and so here as well. and bear with me with the signs and all that stuff for a little more while, and we'll get some practical explanation for this kind of behavior. If you remember from the previous video, we were able to say that the gravitational acceleration on Earth was capital G times mass of the Earth divided by r squared. And if we go from this form towards something like this, so what we have, minus m g me divided by r, and now we multiply by r and divide by r. So now you can see that we can plug in the g here, the small g. So what we get is minus m g r, and this looks pretty much what we had for the potential energy when we were on the surface of the Earth. The only difference is that we didn't measure the distance from the center of the Earth like we are doing in this case, but instead we arbitrarily chose our zero level, and usually we did it on the surface of the Earth. And after that, because potential energy increases as a function of y, we came to this formulation that gravitational potential energy would be mgy, zero level being at the surface of the Earth. This makes calculation simple when we are on the surface of the Earth, but when we are somewhere usually further away from celestial objects, it turns out that it's in fact simpler to use this one. Regardless of what is going on with the signs and definition of zero levels, what we saw was that the gravitational potential energy on Earth, this one, is just a special case of the universal gravitational potential energy. Just like Newtonian mechanics that we have been studying so far are just a special case of Einstein's general theory of relativity. Here on the left, we have plotted this u function. So this is minus gm me divided by r. And because of the negative sign, this means that the gravitational potential energy is always negative. It gets very close to zero when we are far away from the Earth. So essentially this is saying that once we get infinitely far away, then we have zero gravitational potential energy. And when we are infinitely far away, we have escaped the gravitational pull of the Earth. And what does it take to do that? We can answer that question by using conservation of energy. So how much kinetic energy we need somewhere on the Earth to send this astronaut to infinity, that is, escape from Earth completely. So the kinetic energy that it is given must exactly cancel the negative potential energy in such a way that the total energy will be zero. So we have kinetic energy half mv squared. So this is the velocity given probably by a rocket, so that not by a single impulse like a cannon, because the astronauts wouldn't survive it. But as long as it has this amount of kinetic energy and this amount of velocity, then it will indeed escape Earth. So let's put these other terms in. So like this, and as usual, the masses of the astronaut cancel, it doesn't matter what is the size of the object that we are sending away. And if we solve for v, we get square root of 2 times gme divided by r. And that is the distance from the center of the Earth again. And let's say that we are on the surface of the Earth, not here, but our rocket is waiting to be launched from there. So we have to escape from the distance of radius of Earth. If we put in the numbers that we learned from gravitational constants and mass of the Earth, we get about 11.2 kilometers per second. And this is known as the escape velocity from the Earth. No matter what the direction, if we shoot a projectile at this velocity, it will leave Earth and will never come back. And this is pretty much what had to be done to go to the moon, for example. We had to escape the gravitational pull of the Earth to reach the moon and fall under the gravitational pull of the moon itself. As a side note, Reverend John Mitchell in the 1700s asked an interesting question. What if the object is so massive that the escape velocity exceeds that of speed of light? In other words, not even light could escape the gravitational pull of that object, and it would be invisible. And that led to a concept called the black hole. And although the black holes haven't been observed directly, there is building indirect evidence that they indeed do exist, and there's a massive one in the center of our own galaxy.
We're going to take a trip back in time. Are you ready to get into your time machine? Okay, fasten your seatbelts. Are you ready?